Hello everyone, welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. So today I thought maybe we can take a look at how can we do to measure currents. And I'm not talking about current measurements in terms of us as electronists taking a multimeter and measuring currents with a multimeter so that we can see its value, or a current probe and attaching it to an oscilloscope and getting to see the waveform. I'm not talking about those kinds of current measurements. I'm talking about when we have a circuit that needs to measure the current that another circuit or another device is consuming. Okay, how can we measure some current depending on, well, the specific context in which we find ourselves? So let's discuss a bit about what our options are. First things first, we start with what we have or what we consider to have. Well, we in the most simplest form, we have a voltage source, which can be a direct current or an alternative current, depending on the case. I've drawn both of them here. I've drawn a battery symbol to symbolize a direct current source, the direct current voltage source, actually, I should say, and this symbol with a sinusoid for the alternative current source. Anyway, we have a voltage source, and in its simplest form we have a load which we can symbolize by just a resistor, and of course two wires or two circuits that conduce that allow the electricity to flow from the voltage sources to the load. So with this in mind, we are going to see what we can do to measure this current that flows through here. So we have three, as far as I know, we have three options. We can use a shunt resistor, we can use current transformer, or we can use Hall sensor. So we'll take them one by one and we'll talk a little bit about all of them, although I won't be talking a lot about Hall sensors because I would leave that for a different topic, a different video. We will talk mostly about shunt resistors and current transformers, and in the second part of this video, which is going to be a very practical part, I will show you how I built a cheap and simple current transformer that is good enough for some rough measurements in such circuits. So probably the simplest solution would be to have a shunt resistor. We are basically using Ohm's law that states that when a current passes through a resistor, that resistor will have a voltage across it, which is directly proportional to the current passing through it. I don't think we can have anything simpler than that. So we would basically need to insert a shunt resistor in series with our load. It's probably also the cheapest solution because, well, what can be cheaper than a resistor, right? It's true that it needs to be a somewhat power resistor. How powerful, well, depends on the current and its value, but anyway, even so, it cannot get to be too expensive, so it's probably the cheapest solution that we can have. Another advantage is that it works equally well in both DC and AC. A resistor doesn't care about the current that passes through it, so yeah, that's definitely a pretty big advantage. And the fourth advantage is that it is the most precise of all measurement methods. the higher the current grows, the higher the voltage grows on the resistor, and vice versa. And basically the voltage across it tracks the current very, very well, so you probably don't get a better precision than that. However, it does come with a few disadvantages, and that is, well, it cannot always be implemented. There are a few reasons why you sometimes cannot implement this option. If this is a circuit that you are designing, then most likely you will be able to implement, because yeah, you can just take this shunt resistor into account and calculate all the other components based on the fact that you have a shunt resistor and therefore an extra voltage drop in there. So you will most likely be able to use a shunt resistor in your designs. However, if you need to measure something that you didn't design, something that you didn't build, then it's very much likely that you won't be able to put a shunt resistor to measure its current. First, because maybe the voltage on the load will drop a bit too much, because the entire voltage will not be applied only to the load but to the shunt resistor as well. The higher the current, the more this voltage is being kept by the shunt resistor, so the less voltage appears on the load, and well, depending on the load, that might have a problem. Another reason is because this method is very invasive. You literally need to break apart a circuit, a cable, or I don't know, something like that, in order to insert there the shunt resistor, and that just might be impossible. That might be completely unrealistic. And the second disadvantage, which is also pretty big, or it can be pretty big sometimes, is that the signal that we get, which is the voltage across the shunt resistor, is found at the current circuit's potential, right? So if the current circuit that we're trying to measure is this one with the voltage sources and the load, and we put the shunt resistor in order to get its voltage, in order to feed it to another circuit that we want to, measure this current, well, we're going to be working with the potentials that exist in the first circuit. So if the first circuit is, I don't know, a 220 volt circuit, right, that we just plug into the wall, then we will be working with dangerous voltages. That could be a problem. Maybe sometimes it's not a problem, but depending on a case, that could be a problem. It also could be a problem not necessarily for us humans operating the circuit, but it could be a problem for the actual measurement circuit that takes this voltage and tries to do something with it, because it might not like the voltages that it needs to withstand. So yeah, that could be a serious problem that basically disables us from using this kind of method. So we have two other methods. The second method is with current transformers. Well, this is somewhat of a compromise solution, but it's pretty good in certain situations. Sadly, it only works in AC, it doesn't work in DC. That's why I removed the symbol for the battery here and I left only this one. We need to have, and we need to want to measure alternative currents, not direct currents, because a transformer does not work in direct current. The idea is that according to electromagnetism, an alternative current that flows will generate an electromagnetic field that can induce another voltage in another coil, another inductance, right? So basically by having such an inductor created on a toroidal transformer, and by having the initial current pass through that toroidal transformer, we get to have a second voltage that's completely isolated, that is proportional to the current in the first circuit, and with which we can work a lot easier. So this method has what I would call a medium complexity. It's not as easy, as simple as this method, but it's not as complex. It doesn't need such a complex circuit as what we would need with using Hall sensors. So I said, okay, it's I would see it as a medium complexity solution. It's neither an advantage nor a disadvantage. It's somewhere in the middle, right? An advantage is that it has higher chances of being implemented than the shunt resistor option. Meaning, if we sometimes cannot insert a shunt resistor in the circuit that we're trying to measure due to various reasons, there are much higher chances that we can actually do that in this method. So I'm gonna make a drawing for you to understand what needs to be done. Let's say that you have a circuit like this, right? And there's a current passing through here, and you want to measure this current. And of course it needs to be an alternative current. Like I've said, it cannot be a direct current because it's induction doesn't work in direct currents. So you need to do somehow to have this wire. Let's say that this is a wire, right? You need to make it pass through the center of a toroidal core. And of course this means that you will need to break this wire in order to basically insert it, or break it, or desolder it, or disconnect it, however you can, in order to insert it through that toroidal core. And sure, of course, that at first glance could seem a bit of a problem. However, it's relatively easy to just connect a second wire in parallel with the first wire, right? So that when you disconnect this wire, it won't be a problem for the circuit. We're specifically talking about circuits where you just cannot unplug them, right? And you cannot perform this method, these operations unplugged. You have to perform them while live. Well, it's not impossible to create a second circuit in parallel so that current will still have a path to flow, and then cut the first wire and put a new wire, or insert the existing wire through the toroidal core, and then once the new connection is made, remove this extra wire that you put just temporarily, and that's it. That's the operation that allows you to start to measure currents. And then of course you will have two wires coming from this the winding of this toroidal core, toroidal transformer, and that's it. You can start measuring your currents, right? So this is a lot more achievable than trying to put a shunt resistor in series. That's why I said has bigger chances of being implemented than the shunt resistor option. Another advantage is that the signal is completely isolated from the measured circuit. Like I said earlier, the signal, which is basically this voltage created through electromagnetic induction in this coil, has no electrical connection to the original circuit, right? Another advantage, which I will show you when we will get to the workbench, is that this can be made manually. This toroidal transformer can be made manually. Sure, it can be bought, but it can also be made manually, and for certain applications it makes more sense not to pay for an actual current transformer, but to just create it yourself. However, if you do decide to buy it, then the costs can be higher than with the shunt method and can become significant. It's not it's can, meaning it depends, it depends a lot on what kind of transformers do you want to buy and how much do they cost. Now, if I am to go to the nearest relatively big electronic component supplier that's relatively close to my country and that also sells in my country, and if I go to see current transformers sorted by price and only the ones that are still in stock, I get to see that the cheapest transformer is about 3 euros, the equivalent of 3 euros, and the price goes up pretty easily. And within a single page of 20 products, we can clearly see about 11 euros for a single piece of such a current transformer, and of course the prices go up, and you can even have to pay something like 300 euros or more for the absolute best that they have. Anyway, of course I've ignored all the other specifications which do matter, but the idea is that the costs, depending on the situation, can definitely be higher than the shunt resistor method, which requires only a resistor, basically. The other advantage is that it works only in alternative current, like I said, because the induction does not happen in direct current, and also precision differs in function of the transformer quality. Of course, a transformer that we buy has bigger precision than a transformer that we build for ourselves, and of course the price also influences precision one way or another. But fortunately, we don't always need high precision measurements, especially if we only care about the value of the current and not the shape of the waveform itself. Then this might not be a problem. Okay, so we're going to take a look at this option and how I was able to build such a transformer, what you would call a do-it-yourself transformer, shortly. But at last, let's talk a little bit about Hall sensors, which, as far as I know, are the third option that we have to measure some currents. Hall sensors basically pose, they give advantages from both the previous options, from the shunt resistors and current transformers, meaning that they work both in DC and AC. The signal is completely isolated from the measured circuit, and implementing the measurement does not require any changes to the measured circuit, not even the ones that I've shown, which are doable but necessary when we're working with current transformers. With a Hall sensor, we can just take that sensor and place it near a wire where that current is passing, and that's it. The Hall sensor will be able to sense the current flowing through the wire wirelessly, so we don't have to do anything at all about our circuit, about our supply, our voltage supply, or our load. Nothing at all, right? So these are pretty big advantages. However, of course, there are also disadvantages. Hall sensor circuit requires higher complexity. Well, we need to have a circuit for measurement, measuring currents with Hall sensors, and those circuits are relatively more complex than the previous ones we've talked about. They need to take that signal from the Hall sensor and amplify it, and maybe even perform other operations on it in order to bring it to the point where it is usable. So we would need to bother with designing a Hall sensor measurement circuit that has a much higher complexity than the circuit needed with a current transformer or with a shunt resistor. The costs also differ and can be higher than the previous methods. Again, it's a matter of relativity, but if we go to the Hall sensors on the same online shop of this electronic part supplier, we can see that the cheapest Hall sensor is I don't know, something like 80 cents, 80 euro cents, but it quickly goes up to 3 euros, and it can go even higher than that, depending on how good, like you can even have a 130 euro or so sensor, the most expensive one. Of course, each Hall sensor comes with its own set of parameters, and these parameters dictate the costs a lot. One of these parameters is basically at what frequency, at what maximum frequency can that Hall sensor work. And so yeah, costs definitely can differ a lot. Also, depending on a Hall sensor, you might need to have a different circuit, so higher complexity for more difficult Hall sensors to work with, and also the precision differs in function of the sensor and the measurement circuit. So overall, these are the three methods that we can have to measure currents, especially as amateurs in our amateur circuits. So now let's take a look at how I have built a current transformer in order to measure some main voltage load. And well, we need to go to the workbench in order to have that have those explanations, and in order for me to show you how it performs, because I have a small circuit with which we can actually test this method, this do-it-yourself method, and so we can easily see that it is a pretty good solution that is very handy for us. Right, so I will be jumping back and forth between picture in picture, the oscilloscope camera and this workbench camera. Depending on however we might need it. For the moment, let me explain what we have here shortly, and then I'll explain how I built this particular current transformer. So we have an actual transformer that takes 220 volts on the input and gives 9 volts on the output, and a bit more than 10 amps, but we won't get there. We have a shunt resistor for the sake of seeing the current very clearly on the first channel of the oscilloscope. And we also have a current transformer which is connected to the second channel of the oscilloscope, so we can compare the measurements. And on the right end of the screen, but outside of the screen, I have a very rudimentary artificial load where I can basically set a few power resistors on and off, and in function of what resistance I set over there, I will draw a smaller current or a larger current in this whole circuit. And of course we have a multimeter here set to measure this AC current, so we can have a clearer measurement on top of actually seeing the waveforms themselves on the oscilloscope. Now, a bit of explanations about how I built this current transformer. It's very easy, very cheap, and very simple. So you need metal washers. The washers that you can find in hardware stores that you use when you're screwing something somewhere, like, I don't know, maybe in a piece of furniture, and you want that that force from the screw to be more evenly distributed on a larger surface, and you would need you would use a washer in that situation. Well, yeah, I've used those kind of metal washers. It's not my idea, of course. There are people that have done this way back. I'm just showing you this in case you haven't got to see those videos, or in case you saw them, but I don't know, maybe some things were unclear. I hope I can provide enough information so that you can understand what you need to do, or at least what I have done. So I've taken 4 washers, and 4 is a very arbitrary chosen number, that have 8 millimeters internal diameter and 16 millimeters external diameter. The internal diameter is very important because we need to pass, first of all, we will need to wind a bobbin, a coil, right, along this toroidal transformer. And second, because on the inside of the hole we will need to pass whatever wire we are having the current that we want to measure, right? So of course, depending on the thickness of that wire, this hole needs to be bigger, or it can be smaller. Anyway, I found that 8 millimeters is good enough, so I can put I don't know, 1.5 square millimeter cable, or I think even 2.5 square millimeter cable on the inside, of course with its insulation. So 8 millimeters is pretty good. It shouldn't be too large, because then the whole magnetic field might not work as well. Anyway, it should also have enough metal, because of course you want that magnetic field to be generated, and you want the induction to work good enough, right? So for me, these 16 millimeter by 8 millimeter washers were good enough. So I've chosen 4 of them so that I have a decent thickness. Surely they would have worked with less, and they could also work with more. I chose 4 arbitrarily because I found it would be a decent thickness, right, in the end. I didn't want it to have all of them touch themselves electrically, so I put insulation tape between each of them, and then I put some more insulation tape at the end to hold them well together. And of course, in the end, I had to take a small scissors and cut the middle part, so that I still have a hole in there, so that I can, you know, push things down the hole. And the next thing that needs to be done is take enameled copper wire, as thin as you can get, and just wind a coil as evenly as possible, although that's not too big of a deal, and I'll show you in a moment that mine is not even at all. But anyway, do your best to wind that coil as even as possible around the entire circumference. And I have chosen to give 100 turns. Again, it was an arbitrary chosen number, but it turned out to be pretty good. The idea is that, of course, it could have worked with fewer turns, but you don't want to have too few, because the voltage then, especially at small currents, will be very, very small, and it will be difficult to work with. I would say that 100 turns is the minimum. And I will show you shortly, you know, what voltage does it give for various currents. And yeah, and I've chosen 100 turns because that was close to the whole length of wire that I had, which was, I didn't choose a brand new wire. I chose a wire that I recovered from an old transformer. Anyway, this is up for experimenting for you when you build your own current transformer. I'm just telling you, what I've done. I'm showing you the results, and you get to see if you have the patience to turn 100 turns here or not, or maybe you want to put some more. The wire should not be too thick, because then it will occupy a too big space and you won't be able to give as many turns. And also, we're not looking at drawing significant current out of the coil here, right? We only care for the voltage, because the voltage is proportional to the current that goes in the conductor inside the toroidal core. So you can easily choose the thinnest wire that you have. I don't know exactly what I've chosen. It's somewhere between 0.1 and 0.2 millimeters. I didn't bother to actually measure it, so it can be anything: 0.1, 0.15, 0.18, whatever. So yeah, that's pretty much it. It's not a big philosophy. Let me unplug this so I can show how it turned out for me. Right. So you can clearly see the black is the insulation tape, which is a standard electrical insulation tape, nothing fancy. You can see the winding, which is not ideal, not very uniform, but it doesn't matter. And if I tilt this something like so, you can see the extreme washers in a particular corner where there is no insulation tape, but still they are insulated between them, so that's what it matters. So that's what you get in the end. And right, so in this circuit I will choose to put this shunt resistor terminal through this hole, because it's easy. And so this is how I will use my current transformer. And I will plug everything back. Just give me a moment. And then I will switch to the oscilloscope. And as a matter of fact, before switching to the oscilloscope, I will just go ahead and connect my load. Yeah, let's see. Click. Of course, I should power it up. Right, and so right now I'm drawing 600 milliamps from this entire current, entire circuit. And here we see, let me make it a bit bigger, not so big. Right, so the blue channel is the voltage on the shunt resistor. I have a 0.1 ohms resistor, so basically for each amp that flows I will have 100 millivolts across it, and this gives me basically the reference waveform, because like I said, the shunt resistor gives the cleanest waveform of the current. And with yellow I have my do-it-yourself current transformer, right? I've flipped around the channel so that I get to have this sort of well, actually, now that I've yeah, hold on. Yeah, okay. I flipped the wires before, so now I should see them better like this. Okay, so of course there is some phase shift between you know, the induced current and the actual current that flows through our circuit. Also, there is some form of DC offset. Don't ask me why, because this channel is coupled in AC. Theoretically, it should wiggle around the zero line, but anyway, we'll just ignore that. So we see that at 600 milliamps, which is, by the way, let me activate the measurements. This is something that we can also confirm with the oscilloscope. We have about 60 millivolts for RMS value for the blue waveform, which is the voltage on the 0.1 ohms resistor. Therefore, we have 600 milliamps, right? Which is exactly what this device tells us. And for 600 milliamps of current, we get about 9, maybe sometimes 10 volts peak to peak signal on our current transformer. I chose to measure the peak to peak voltage because it's easier to see than the RMS voltage. And besides, we will probably use this voltage later in a circuit, and we will probably rectify it and filter it a bit so we get only a DC voltage depending on the current. Anyway, we will have this in that circuit. We will be looking more at the peak voltage rather than the RMS voltage, most likely. So anyway, let's move up the current. Let's have it draw some more. Just a second. Let's go. Yes. Right. So I have about 1.4 amps right now, and let me scale down these waveforms. Okay, so now again we can confirm the value of the multimeter, about 1.4, on the oscilloscope about 136 millivolts times 10, that's milliamps, right? So 1.37 amps. And for this, our do-it-yourself current transformer gives about 27 millivolts peak to peak of signal. By the way, the increase is not linear. The transformer's response is not linear. Sadly, it's a little bit exponential. The more current we draw from the initial circuit, the higher the voltage grows, but not linearly. At double the current, we get more than double the voltage on this particular transformer. Again, it most likely matters a lot how I've built it. Anyway, it's good enough for me because, again, I don't plan to use it for some precision measurements. I will only need it in order to detect when a certain current will pass a certain threshold. So before actually putting it in the circuit, I will be able to test to see what voltage do I get there on the transformer, and then I will be able to simply adjust my measurement circuit accordingly. Anyhow, let's try to push a little bit more current in our circuit, and let's see. Yeah, I'm gonna go probably full speed ahead, so to speak, and see. Yeah, so I now have almost 4.5 amps, and it's probably gonna be the last test I'm going to do. 4.5 amps almost, and the waveforms look like this, and measurements tell me that indeed I have about well, this says 4.3 amps, but whatever. And I have about 147 millivolts of signal on my current transformer. And the waveforms are pretty close to each other, right? Ignoring the phase shift, the waveforms are pretty close, I would say. So at least at 50 Hertz, this method, this do-it-yourself method, is it would be decent even for you know, having a measurement of the actual waveform and getting to see how the current looks like in your circuit. It's not that bad, it's not that unusable. Anyhow, by the way, this channel has had the bandwidth limit on so far, but well, even with bandwidth limit off, it's not it doesn't get so much uglier. So yeah, that's pretty much it. I hope you now understood how you can build this for yourself, and I hope you understand now that this is well within our power. I'm going to I'm going to shut it down so that I don't burn my resistors. It's a good option, it's a good method, and it's well within our power to use it. Since these are a bit, what I would call a bit exotic components, we would probably not like to buy several of them and make a stock at home. I mean, it's not like transistors or resistors which can be used everywhere, right? So you can easily buy a large quantity of them, and whenever you need to use it, you just use it. When it comes to current transformers, well, you don't use them all that often. So it doesn't really make sense, especially considering their prices. It doesn't make sense to just buy a whole lot of them and have them laying around. Unless you have a lot of money and you just don't care about it. But anyway, on the other hand, it's not a problem to buy a lot of washers, right? Especially since washers can be used on other projects as well, even projects that have nothing to do with electronics. They are relatively cheap. They are sold by the kilogram. Same with insulation tape. That's also pretty cheap and it's not a problem. If you also have some old transformers to recover the enameled copper wire from them, then you have everything that you need. So for just I don't know, simple circuits to detect the current passing above a certain threshold, this method is perfect. So anyway, thanks a lot for watching this video. I hope you enjoyed it. Those of you who can and want, I welcome any form of financial support on Patreon. By helping me, you are helping yourselves, because I can learn faster, and so I can come with new videos faster and teach you as well. Of course, you can also leave comments and suggest various topics, and provided that I can, I will make some videos on them. So thanks a lot for watching, and hope to see you next time. See ya!